supposed to have been adult food. And the kids were really gracious about that. We're all a little hungry, so we're going to have a half-hour break. And I promise you there's going to be food there. I'm going to get it myself. After this, a half-hour break. Thank you very much.
So we are a very ancient math circle. We started in 1994 with this, well, the East was set up for, that's the way it went. And what we do in our classes is that in each class we're trying to recapture as far as possible the conditions under which mathematicians actually work. And what you do is when you are actually as opposed to school mathematics.
Can you hear me if I use this handheld microphone, which I'm totally unused to using? Does this make sense? Okay. Good. Okay. This is addressed to all of you, but I guess the first few words are more or less to the people sitting in rows 3 and on. Those of you who like integers, that means 3, 4, 5. Our belief is that mathematics is one's native language. It's our lost native language, and we can all do mathematics, enjoy it the way we all enjoy music, and that talent is a myth. I'm sure this will come as a shock to many of you. We believe that anyone can not only enjoy mathematics, but do it at the most
it has to do
level.
with expectations. In the Navajo community, there is no tone deafness. It's just assumed that everybody sings. Everybody starts singing and everybody continues singing. You may be a great singer, you may be an okay singer, but there's not the sort of thing that I encountered in my high school classroom where a girl came in with a note from the doctor excusing her from mathematics classes because she had a brain unfit for math. That kind of blanket statement is simply outrageous. I mean, everybody has every possibility, and you can try them all.
And what we want to do is do with you guys what mathematicians do. We want to work with you the way working research mathematicians work, which is collegially, not competitively, working with one another, playing off one another's ideas.
That's why we have you sitting around like this, so that you can talk back and forth.
In a math semicircle. and also with no time pressure, no kinds of problems where you've got 10 minutes to get this done. You've got all the time in the world. We don't have to get anywhere in particular today. Where we do get, we'd love to get some great ideas from you and then try to prove them, discover the idea and then invent a proof which will anchor it into solid thought so you know this is true or false or both.
So we're going to pose a problem, and we'll pose it very loosely, and then it will get further defined as we talk about it. And just take it as it comes.
So at ease socially and intense intellectually. Nice combination, like chocolate syrup, hot chocolate syrup on ice cream.
Anything else we have to say?
Yeah, I guess one thing we should make clear to the older audience, ours is not a method. A method is something which is imposed on a problem, imposed on an audience. Ours is an approach, and it changes it's responsive to the particular problem and the particular people here. That's why we don't know what's going to happen this afternoon. We have something to start with, but we don't know where you guys are going to take it. And we'll go along with what look like good lines of thought. And if we come to the edge of a cliff, we'll try to haul you back.
Or go down with you.
The topic should be challenging, but it should be interesting. It should be an accessible mystery. It should be something which is really intriguing, but which we can really get our hands, our minds on and around.
And we have lots more to say about what we do, and it will eventually appear in the book that is going to be published by Oxford called Out of the Labyrinth, Mathematics Set Free, and that'll probably appear in the fall. But we'll probably be also saying, oh, and by the way, there was another thing we should have said, which we haven't mentioned, and it'll keep on going that way.
You're now speechless, so I'll speak. A book that we've written called The Art of the Infinite has chapters in it which come from our Math Circle classes, and I hope you'll enjoy it, all of you. It's accessible, full of mysteries that are accessible. So look, enough of a preamble. Why don't we start thinking about
this. I killed it. If I speak
Help.
loudly, can you hear me?
Yeah.
Great. I'll speak.
we can pass this back and forth.
I'll be the one who shouts.
But we need that for the recording.
You do. So what if we just pass this back and forth?
Does this go on the recording too? We'll pass it back and forth. Okay. Doesn't sound as if I'm making a loud noise. Because this is a very advanced math class in a very advanced mathematical institute. We're not going to start with something childish like what's 1 + 1. We're going to start with something much more advanced. What is 0 + 1? Do we think so? We're really sure?
Yeah.
And what is 0 + 1 + 2?
3.
And now, what's the next question I'm going to ask?
0 + 1 + 2 + 3.
Oh, you're so good.
Do we think we have got this completely doped out? And we have a pretty good idea? But what about this 0? Is it necessary?
No.
Why not? Good.
It's nothing.
It doesn't do anything. 0, useless is an excellent term for 0, or at least not dangerous as far as 0 is concerned. When is 0 dangerous? Yeah.
After something?
When is after something?
Nice idea. Like 1 is different from 1 with a 0 after it.
Yeah.
Because 1 with a 0 after it is bigger than 1.
10.
In fact, 10 times bigger. Right. Good. Oh, what's the product of all the numbers multiplied together? Every single number in the world multiplied together?
5.
Why? What a nice idea. Why? It sounds good. Well, how about this?
We have an idea over here.
Yeah,
Infinite because there are infinitely many numbers.
that's great. It would be infinite because there are infinitely many numbers going off that way. 1, 2, 3, 4, 5. Yep.
There's even infinitely many numbers between 0 and 1.
In fact, there are even infinitely many between 0 and all those fractions trapped between 0 and 1. And they're also the ones going off negatively. You multiply all these together, you're going to get some humongous number. Sorry, what's between those positive ones and the negative ones? 0 again. So if you multiply all the numbers, yes?
You get 0?
You get 0. Yes. Because all those positives times all those negatives with all those fractions in between is going to be something, but then times 0 wipes it all out. Oh, so 0 actually is helpful there. Okay.
Well, helpful or dangerous, depending on what you were hoping for, especially if you'd gone to the trouble of multiplying all the other numbers together first, and then somebody said, oh, don't forget 0, and you were a little bit angry at the amount of time you've spent multiplying all those other numbers together, and off they go.
Did we ever get answers for what these things add up to? Oh, what's the,
1,
yep.
3, 6.
Next.
I'm now okay with you if we move
10,
off.
12, 10.
I heard 9, 10, 12.
10.
The answers I've heard were 9, 10, and 12. I heard 10 several times.
10.
You sure?
Yeah.
10?
10.
Is everyone convinced by this?
Can you prove it?
Yeah, 'cause 10.
6 and 4 is 10?
10. Yeah.
Are we sure, or have we just been told?
For sure. 2 plus
You did something nice. Instead of adding up the 1, 2, and 3 again, you picked up the past result and then just added 4 more to it. Okay, I guess I'm kind of convinced it's 10. What's the next question? Yes?
1 plus 2 plus 3 plus 4 plus 5.
No.
15.
Yes.
10 plus 5.
No. What do you
Yeah.
think?
10 plus 5.
10 plus 5.
What do you think?
I think 0 plus 1 plus 2 plus 3 plus 4 plus 5.
Very like the other possibility. Actually, we're being perverse. We're not going to add just 1 plus 2 plus 3 plus 4 plus 5, but we're going to add up to... What do you think, Ellen?
Let's go to 100.
Let's go to 100. Yeah, 1 plus 2 all the way up to 100. How much is that? Eli?
50,000.
50,000. Sounds right to me. That's conjectures. My handwriting is terrible, but that says conjectures. So conjectures for adding up from 1 to 100. One conjecture is 50,000. Yes? 5,050. Others? Oh, come on. Wild guesses. What about I?
I'll put it in.
Good. Why 5,000? 50,000 rather.
Because 99 plus 1 is 100, and 98 plus 2 is 100. And if you keep going, then you're going to have 50. 50 plus 50. And then you're going to have 50 hundreds, and that's 50,000.
That's a neat idea. You're not just going to start adding from the beginning the way we've been doing, but you're kind of pairing them in a nice way. Yeah, Ben.
Eli, you said adding 2 50s?
No, I said, yeah, if you have 99 plus 1 and 98.
Yeah, I get that,
plus
but when you reach 0, when you reach 50, there's only one of it.
Oh.
I think you
Whoa.
add 50 plus 50 to get another 100.
50 plus 50.
But
Okay.
Ben is saying you've only got 150 in
Hold
this.
on.
Yeah.
We got some confusion.
Yeah. Yeah. So am
Okay. Give us a question, and then give us an answer.
I just don't get it.
Oh,
Okay. I think
well,
Eli.
Do you know any way of adding them up, like a depressing way?
Times.
Well, no, like just simple brutality.
I mean, the way we were doing it is
Like we added 1
plus
plus 2 plus 3.
6, and 4 more is
6,
10.
And 4 is 10, and 5 is 15, and 6 is, it's getting hard, there's carrying.
And an
and
important
7
thing
is-
about math, is if it's boring, you're not doing it the right way. Yeah.
That is a general rule. If it's
Yeah.
boring, it's not math.
Before Nina, what were you going to say?
I know what 6 is. 21.
When you
21.
get 6 more and you get 21. Nina, what were you going to say?
Okay, like Ben was saying, there's only 150. There's 250s up to 100.
If you add from 1,
This
Up.
I think, is where we were when it began to get confusing. Which is that if you added
There are 250s and 100.
1 and 100,
I see what you're saying, Nina.
what do you get?
101.
And then he says, add 2 to 99.
101.
Ha-ha!
Oh, that's weird. Sheer chance.
That was his sneakiness.
Is that what you had in
That's-
mind? Was that the idea?
It was Eli. Yeah.
Yeah, Eli, is that your idea?
What I know
Or did you say 2 plus 98?
is 100.
Yeah,
Oh.
yeah. I think 2 plus 98 is 100.
Okay, let's do it that way. Sorry. 2 plus 98 is 100.
And then, yeah, Ben,
I think it's 550.
550. Okay. Interesting that all your guesses, except for the I that we threw in, start with 5s. So they're, well, if you go by majority vote, looks as if a 5 is important here. Yeah, Ben,
I think the 5050 is the correct one.
why?
Because there, it seems like there would be an extra 1 on the end. So, see, when you add 100 plus 1, 2 plus 99, you get 101. So if you do that 50 times, the one becomes 50, and then the 100 becomes 5,000. So 5,050.
Is that making sense, Elena?
Okay.
Why 50 times?
I'm just guessing that that's how many times you would do it, because
It's a nice guess.
there are 50 pairs
Oh, that's great.
1 and 100.
Of course, you're right.
So we've got two methods here, aside from the brutality method of just adding until we die of old age. We've got Eli's method, which is finding hundreds. So he's got the 2 plus 98, and the 1 plus 99, and the 3 plus 97, and he's getting a collection of hundreds. And the question is how many of them? And then we've got Ben's method, which is the 1 plus 100. And the 2 plus 99, et cetera, et cetera. And what's he getting?
Each time. Yeah.
He's getting
101.
101s.
Whole bunch of 101s. Of course, it's possible that there are two different answers. These two different methods will give us two different answers. It's also possible it's undecidable. Yeah, Nina.
You know, for you just did 1 to 99, you could just put a 0 at the end to get 0 plus 100.
Oh, what a nice idea. Bring the 0 back in. Is that what you're saying? So we can make
Well, so
pairs.
we get another.
Well, it looks better that way.
Yeah,
to
it
make
looks better.
Nicely symmetrical. So we put in a little Nina bit here, which is 0 plus, and then you get to connect all of them.
How many pairs? How many pairs would there be that way?
That's where we've got a problem. We've got a little cloudy bit in the middle here.
Yeah, what do you think? 48 pairs that way. 49, something like that. Yes?
Wouldn't it be 51?
51, 48, 49, 51. Sounds like something around there. 51.
I'd say 51. I'd say 51.
51 pairs. Each pair has two numbers in it.
Yeah.
One of them is 0.
So we have guesses of 48,
49,
49,
51.
51.
Yes.
For Eli's method, there should be 51.
For Ben's method, there should be 50. Yeah.
Oh, fantastic. Why?
Well, because there a half of 100 is 50, and then half of 100 being 0 is 51.
It's really nice.
I mean, no, because
Half of 100 is...
because in Eli's method, then it would be an odd number, so it'd be 51 and 49.
So odd numbers are causing a little bit of problem
That's
here.
why, isn't that why Doosan thought it was 49, and then there's
Yeah,
40,
yeah.
51 too?
Is that why, Duxon? Yeah.
You can't throw it 50.
Right.
Yeah, this is definitely cheese stands alone
Yeah.
moment. Yeah.
Can't pair up 50 if you've got an odd number of them. Is that the idea? Or you get a whole bunch of 101s over hundreds. So, by the way, which of these answers is looking good, or are none of them looking good now? Ben?
I'd still say 5,050, and for the pairs,
Yep.
I'd actually say 50, because there are 1 to 100 numbers, so that there are 100 numbers, but then if you add 0, there are 101 numbers.
Yeah.
So one of those pairs would only have one number,
Right.
but there can't be a pair out of one number, so it would count as a pair.
Great.
So there are 50 pairs with one number left over, which you just add by itself.
Good. 50 pairs with one number left over, which you just add by itself. 50 pairs, each one of worth is which is worth how much?
It could be 100 or 101.
So 50 pairs, each one is worth, what'd you say, 101?
101
Each-
or 100.
Well, this is nice. We've got two ways of doing it. You can either say we have got pairs which add up to 100, and then we've got 50 left alone by itself. And how many hundreds do we have?
You've got 100 by getting, I'm confused. Which one are we doing, 101 or 100?
Well, this one we're doing it with 100, and we're having
Okay.
50 standing left.
Like the cheese, which stands
Right.
alone.
Down here,
Okay.
we're doing it with hundreds and ones.
Which way would you like to do it? We can do it by both ways, or what do you think, Nina?
I think it's kind of complicated both
Oh.
So they're both complicated, but in different ways. Because that one, the answer has an extra one hanging off, and Eli's way, there's just one by itself.
Uh-huh.
So it would be nice if we can come up with a way in which it's clear
But
how many additions we have.
How many pairs?
But also for Eli's way, there's only one left over. For Ben's way, there'd be many 100 ones.
There'll be many 100 ones.
And there were for Eli's way, there's just one.
Okay.
Now they got it like
Yeah.
So we have many times 101. What does this equal? Many times 101 is many 101. Yes. Just get rid of the time sign. It sounds so nice. Many 101. What's the many? When you've got the 1 with the 100 giving you 101, the 2 with the 99, etc. If we can just figure out how many the many is, yes, Ben.
50?
50 of the 101s. By the way, before we do this out, does it look like any one of the things on here?
Erase 550.
Erase 550. Erase 50,000. Okay, reluctantly. What about I? Should I erase I?
Yeah.
Okay. Yeah, Eli.
Why 101?
Why 101? Good question. Yes, why, Elena?
I have an idea because, like, maybe I'm not sure, but 51 is half of 100,
Hmm.
and 50 is half of 1.
Yes. Nice. By the way, it often happens when you're doing a hard problem that you begin by saying, I'm not sure of this but, and often your subconscious comes up with some really good ideas. So don't hesitate to make wild guesses and say, I'm not sure of this but. That's a nice idea.
Remember when we started and we were saying we think we know how this goes on? Like after 4, we have a good guess. What's going to go here?
98.
And I've hit the bottom of the blackboard. So I can't write all the rest of the piles I was going to do. But here's 1 pair, here's 2 pairs, here's 3 pairs. So I keep on counting down. When am I going to get to the last of the pairs that I get to make?
50.
50 and its friend 51. And they will be the last. So the question, this will tell me how many pairs.
50 pairs.
If
Well-
we had blackboards, it went all the way to the floor.
The great thing in doing math is you try to simplify, you try to make it simpler and simpler and simpler, which we did. Eventually, you've got to do a little bit of work. And we've gotten to that point. We've got to now multiply 50 times 101. Ben. No.
Don't trust
No,
a calculator.
you've got one. It's between your ears.
Never trust a calculator because the more important it is, the more likely you are to hit the wrong button.
Or the batteries died.
5,050.
You mean? My gosh.
Yeah.
How, did you multiply? Did you do it this way, or did you do it that way?
Or did you do it this way?
In your, okay.
Yeah, I did it in my
That's how I
head.
did it, and then I added. That's how I did it too.
Okay, great.
That's in here.
This way?
I did it that way too.
That's all that fits in my head. I can't carry in my head.
But this is terrific. Yeah, Nina.
You would have gotten the wrong answer if it was 50 or more.
You would have gotten the wrong answer if it was this one. You're probably right. Let me just check. Well, let's see. 1 times 50 is 50, and then there's this 0, and then 1 times 50 is 50. Oh, I think it worked out. It's weird. It's weird to have the larger one on the bottom.
And slipping that
But
zero in, I think, is totally untrustworthy.
I just did 1 times the top number, then 0 times the top number, so I put a 0 in there to tell me to move over 1 more unit when I do the next one. See, it would be in a lot of times, yeah. I think 3 times 4, for example, which is more or less 13. Well, 12 is more or less 13, is pretty much like 4 times 3, which is kind of 11. Kind of. It's that kind of. I hope it doesn't matter. Well, I don't know. Does it matter in which order you multiply numbers together? Could you get a different answer other ways? You might get a different answer. No. How do you know it doesn't matter? Yeah, Laura. Same numbers, just in a different order. In other words, 3 times 4, I could have pictured 3 times 4 as 4 rows of 3 dots, 3, 6, 9, 12, or I could have pictured it as 3 columns of 4 dots, and 3 rows of 4 would be the same as 4 rows of 3. So I guess it doesn't matter which way you do it. But you're right, Nina. It's a little trickier or uglier when you put the larger number on the bottom. It's a lot uglier. From now on, multiplication must be done with the larger number on top, especially if both numbers are the same, have the same number of digits, like 75 times 37. You've got to put the larger one on top. Yeah. Okay. We would certainly never want to do that. Yeah. Okay.
I have a parenthetical question. If you're, is it always okay to do things in any order you want? Like you can do 3 times 6, or you can do 6 times 3. What about adding?
Guess what?
Well, I was gonna,
Yeah.
Yeah.
I was gonna say about dividing. You can't like,
Oh.
it's a different answer. You do like 5 divided by 2 and 2 divided by 5.
Oh, you know, you're right. 5 divided by 2 and 2 divided by 5, they do come out differently, don't they? One of them is certainly bigger than the other. So it matters with division. Yeah, Eli.
Also subtraction.
Really? Give me an example.
Oh yeah, like 2 minus 5 and 5 minus 2.
There's lots of 2s and 5s in this story.
Well, this one I know is 3, and that one is negative 3. That's why they're different. You're right. You're right. The size is the same, but the sign is different.
So which would you prefer to have?
They're not the same amount, right?
Look sort of similar. Or it looks plus 3 and minus 5.
Yeah, okay, good. That minus 3, 2 minus 5 is negative 3, reminds me of a very odd thing. There are 3 people in a room, and 7 people leave it. How many people have to go into the room before the room is empty? I think that's the right thing to say. What? There are 4, right. There are 3 people in a room, 7 people leave it. How many people have to come in before the room is empty?
That's a mathematician's joke.
Yeah, Ben.
Wait, I forgot what you said.
Okay, Nina.
I mean the joke. I mean, but it really cares.
It's those 7 people leaving the room, which is hard to get one's mind around. I need a number, anybody's number, a number. Somebody who hasn't said anything yet. Yes. What, 5? 5. I need another number, a bigger number than 5. Yes. Okay. How much is 5 plus 6? 11. Okay. Starting with 5, give me a different number. 20,000. Great. Do you know what we're in for? Could you add up all those numbers, please? All the way up from 5, all the way up to 20,000? Oh, how long is it going to take?
A long time.
A long time. Would you like to be more specific?
A few hours.
A few hours. Do you think we can do it in fewer than a few hours?
Yeah.
No. Good. Okay. Just checking.
Because our answer times 20,000. Like that got.
Maybe.
No, I mean not 20,000 times 2,000.
Okay.
So we did 1 to 100.
We did 1 to 100. We got 5,050 by not adding them all up, by not doing it brutally. Ben.
Times 20, because 20, if you multiply the answer, if you multiply 100 times
Gotcha.
20, oh wait, wouldn't it be 200 actually?
So you're saying multiply 100 times 20, which will get you something like 20,000.
And so multiply the answer here
by 20.
20.
Because if you add up all the numbers from 1 to 100,
Isn't it 100 times 200?
ah,
Yeah, that really took 3 hours.
you're saying this isn't 20,000. You're saying we're wrong even here.
Yeah, I think because there's 4 zeros at 20,000.
Oh, okay. So multiply it by 200. So just multiply this answer by 200 and we'll have the right answer. Right? Right? Right?
Yeah.
Never believe authority. Never believe people who nod their heads. It's clear that the answer will be 200 times 5,050, right? No. Why not? Where did the no come from? Yes, David. Right, because you're never supposed to believe authority. There's the answer. So what will it be? Adding up. Oh, you know what? One thing, we're starting at 5 instead of at 1. That's going to change it a little bit. Ben.
It would be whatever you don't say.
It'll be whatever I don't say. There's a huge number of numbers out there that I haven't said. Which one of those is it?
He's not going to say most of them.
Nina.
Okay, if we're doing multiplication, 5 is like not a plus symbol.
Okay, what I meant to write was 5 plus 6 plus 7. But I'll run out of blackboard chalk and time if I write all the numbers up to 20,000. So I'm going to put in those dots.
See the little dots.
The little dots, they are very small.
Just made a big mistake.
Yeah. No, they were too small.
And can you just do stop writing?
Yep. I want to add up all those numbers. Or you want to add up all those. Or you now want to add up all those numbers.
Would that be the same as 5 times or not?
I don't know. Might be.
Because then if you just do 5 times 2.
Is the answer going to be big or small? Bigger than 5? Bigger than 10,000? Bigger than 20,000?
Yes.
A lot bigger or just a little bigger? A little bigger.
Well, it depends on what you say bigger.
Oh, good. It depends on what you mean by bigger.
What do you say?
20,005.
Oh!
5.
When you add up the first number with the last one, you get 20,005. That's nice. Eli?
What about 6 and 7 and 8 and all those?
Yeah, what about
Yeah,
them?
what
What
about-
about them?
You would get way more in 20,000.
It's going to be a lot bigger, right?
Yeah.
Okay, do something with them. Yes, Elena.
Erase them.
I could do that. The answer to this problem is give up. What were you going to say, Elena?
What you want to do is you want to add all those numbers up and then add those two together.
Great, great. Add all these numbers up, and at the end, throw in 20,005.
I
Oh,
agree.
no is
I agree.
right.
Oh, no is
It's-
the very thing I was about to say.
I mean, Elena's idea is great if we could just simplify the add up all those numbers and then. Add up all these numbers, but not in what's going to take 2 hours. Can we do it in 2 minutes? Ben? Ah,
I was thinking going back to that,
yeah.
we could multiply it by 2, which would be 10,100, and then so then you could divide what we need to multiply it by 2, and then if you multiply by something with a 1 and just zeros, you can just add the zeros on the end.
Right.
So we could just add the 0 on the end of 10,100.
Sounds good.
Are
Though
we,
in-
are we still operating on the idea that what we have is 200 copies of this?
yeah, oh man, because
So we just have to take this and multiply it by 200.
You're saying
I'll
from
multiply by 100 if you'll multiply by 2. I'll do the hard part. What's 2 times 5050?
5050.
Yeah, times 2. 2 zeros are 2 fives are
10.
10 and 2 fives are 10. Okay, there.
Now the 0 0.
And then we add the 0 0. I forgot the 0 0.
Right. So 1 million. That's pretty big. But you're saying, aren't you? And you may be right. You're saying that when you go all the way up from 5 to this gigantic number, you're just getting a whole bunch of 1 to 100s repeated. Yeah. Yeah. Yeah.
Wait, there we have a no.
Just getting
You
Show
don't
me.
think it's a bunch of 100 to 100s repeated?
Because probably.
We're going. Could we start from 1 just?
Oh, let's start with 1. Why make it hard for ourselves? Add up from 1 to 20,000.
That's because then what we have here is the idea that if we added from 1 to 100, we know what that is, and then we say then we'll add up the next chunk, and the next 100 numbers will add up to be the same thing.
Right? From 101 to 200 is the same as from 1 to 100 when you add them all up. Yeah? Is a very good beginning of a sentence. What's the end of the sentence?
Maybe.
Maybe, yeah. From 1 up to
We
100.
need an experiment.
Yeah.
Let's get rid of some of the zeros.
Thank you. So many zeros.
Let's look
Okay.
at this. We say
That's a zero.
what?
That's a zero.
What have I done?
On the end of the 10 is a zero.
Oh, no, we're saying adding up the numbers from 1 to 10.
I just want to add the numbers from 1 to 10. Because all of this stuff is getting just too gigantic.
Too hard to think about.
And especially after that excellent lunch, I'm too tired to do all those huge numbers. And
What
so
were you going to suggest?
I was going to say the answer
What?
to that. I know the answer.
What's the answer?
Because they're always 55.
55, which is rather like that 5,050. Well, how'd you get 55?
Because she's done it.
Oh. Should we trust you?
Great. Well, hang on to that, because our argument was that if we took the first 100, and then we took the next 100, and then we took the next 100, we could add up the answers that we got for each of them. I'm going to take the first 2. And what do I get when I add the first 2?
3.
And then I'm going to say, how many groups of 2 numbers are there? 1, 2, 3, 4, 5.
5 times 3 is
So
55.
therefore, if I took 3 and I multiplied it by 5, I get 15. So the sum of the numbers from 1 to 10, ta-da, is 15.
That's not 5 plus 6. No, 5 plus
So where'd I go wrong?
Right. Right. So the idea of just adding up the bunches and hoping that we're going to get a bunch of 55s when we go up from 1 to 100, maybe it's not going to work because of something going wrong with the numbers in between. Yeah, Nina.
I think it is.
You think that this answer is 55? Okay, could we do it in a snazzy way without adding 1 plus 2 plus 3 plus 4? Add what? Add what 2 numbers together? Yes.
You can add 9 and 1.
Could add 9 and 1,
That gives us a 10.
and then
And then 2 and
2 and 8. Another 10. How many pairs will there be of these?
3, 4, 5. Oh, it's obvious it's 55.
It's obviously 55.
It's so obvious.
Oh, okay.
10, 10, 10, 10. That gives us 40. And what do we have hanging around left alone? The 5 there.
And the 10 at
there.
the end. So that works. That works.
55, definitely 55. Now, is 55 the same as 15?
No.
You're sure? And we think 55 is right. Then we have, unfortunately, to say that we think 15 is wrong. So I know I multiplied 3 times 5 right. And I know I added 2 and 1 together and I got 3. I know that was right. So that is definitely 3. I know that part's right. And I know that there are 5 pairs in 10.
But that must mean that to go from 1 up to 20,000, you can't just take bunches of 5,050s, which is what 1 to 100 is. Because if you could, the same argument would have worked here. We would have gotten 15. You see what I mean? No. Okay, here's what I mean, Laura.
See, this time we just took a whole bunch of 3s, and we said if we took 5 3s, because this was 3, and then we said, so this must be 3 too, because it's 2 numbers added together. Am I right?
No.
No. So just because the numbers started with, hundreds and thousands and things like that, to go from 1,000 to 2,000 is different. You get a smaller sum if you add smaller numbers together.
Let's try this. Let's try adding from 1 to 4, which we know how to do. But let's do it the snazzy way. Let's do it the way you invented.
That's all.
Instead of doing 1 plus 2 is 3 plus 3 is 6 plus 4 is 10, there's this other way of doing it, which is multiplication. What times what? Yes. 2 times 3. 2 times because there are 2 pairs?
2 times 3. No, it's just 2 times 3 is 6, and then you add 4, which would be 6.
I see. It's the 2 times 3 plus the 4, then the 1 is sort of hanging out there. I thought we had this nice kind of, I don't know, maybe we didn't, a way of looking at the whole sum.
We were able to hit them with the Ben or the Eli.
Yeah. Yeah, Ben.
Add up the 1 and the 4.
Add up the 1 and the 4, and that each one makes a 5. How many pairs of 5s? So multiplication. So it's going to be 2 pairs, each worth 5. So it's 10. So from 1 to 20,000 is...
10,000.
What are they? What are they?
That's the number of
cents and bats?
pairs. 10,000 pairs. Each one is worth how much? Look.
What do you get when you loop them from front to back? Do you remember about the looping?
Yes. I thought I heard it.
He said
You say 1 and 4
20,000.
makes 5, and 2 and 3.
When you loop,
What?
when you add the first and the last, what do you get?
Sorry, what'd you say?
When you add the first number to the last number,
Oh, because I thought you said you didn't see where. how you could
20,00001.
figure out what
You
were
get
multiplying by
20,001
Sorry.
in each pair,
10,000. You didn't say that?
and you get how many pairs? 10,000 pairs. That's going to be the answer in less than 2 hours, because we haven't actually done it yet. But that's not going to be too terribly hard.
We're not going to do that.
Not going to do it. We could do it if we wanted to. Okay?
It is possible for human beings to do that.
What?
multiplication.
do 1 plus 2 and then add the zeros.
It's multiplying. Yeah. You want to do 20,001 times 10,000. I'll bet we could do it in less than 2 hours if we were really good at it. Yes, do so.
Let's see. Are we adding?
We're multiplying, I'm afraid. Certainly it would be if this were times 1. Yep. But I want it more than times 1. I want it sort of times 10. Well, actually, I want it times 100. Well, by 100 I mean 1,000. But by 1,000 I mean 10,000. I want it that
Mario
neat.
has an idea.
Yes.
You could do like 20,000 times 10,000 and then like add 10 more thousand.
Oh, that's a nice idea. Break it up into smaller parts. Good. Yeah, Ben.
This number has just a 1 and zeros, so you
It
use
does.
the same kind of rule that you do with 10, when you just multiply something by 10, instead of going through the trouble of adding it 10 times, you just add a 0.
Oh, terrific. So how many
So-
zeros should I add on?
4, because that's 4 and 0.
1, 2, 3, 4, and then just copy this number down.
pretty big.
It's pretty big, but we got it in less than 2 hours.
I thought it was going to take a lifetime.
I thought so too. What if we start with negative, give me a number.
7.
Start with negative 7.
Easy one.
Oh yeah. Start with negative 7 and go up to what? 27? 27? Go up to 27. Is that what you're saying? Go up to 27? Oh, go up to 7. Oh, go up to 2.
Yeah.
Okay.
Let's go up to 2.
Let's
I've
go up to
already
2.
gotten to 2.
Now this is a totally different problem.
How many numbers are between 7 and 2?
Good. Good. How much does each pair add up to?
Do they all add up to the same thing?
What?
5.
Sorry, I couldn't hear you.
5.
I'm just having trouble hearing you.
Oh, negative.
Oh, I heard you. Negative 5. Okay.
Negative 7 and 2 makes negative 5. How about negative 6 and 1?
Okay.
Do we think we have a theory?
Yeah.
Negative 5 and 0? Okay, now comes the hard question. How many of these have we? What's going on in this little ... neighborhood where it's all concealed from the human eye? Yeah.
Elena.
They all add to 0? Okay. From between here and here?
We get negative 4 and negative 1.
4, 1, 3,
Negative 1.
negative 4, negative 3,
Negative 2, negative 1.
negative 1,
Negative
sorry,
2.
negative 2. And so we've got 1, 2, 3, 4, 5 of them?
So the
What's it
answer
gonna
is
add up to?
negative 25. You mean we can start anywhere and go to anywhere and this idea is going to work? Yeah? Okay, start with 0 and go up to 0. How many pairs? And what does each pair add up to? And 0 times 0? It seems to work. Okay.
It's pretty good.
Okay. What if somebody walked into the room right now and they hadn't heard all our conversation and they wanted to know what you were doing? How would you describe what we've just done? You're right. We're doing math. And in particular, Genevieve? Very, very complicated math. Though making complicated things simpler in some ways. Nina? Okay.
Come back as soon as
yeah,
the
Ben.
video stops.
We've been adding long sets of numbers together.
Great. Adding long sets of strings of numbers together. Starting with what?
1 and going to, what was it?
I don't know. I've forgotten.
20,000 or
Yeah.
something?
One time we went to 20,000. We started with 1. We always, well, we didn't always, but usually started with the 1. Once we went to 10. Once we went to 100. Once we went to 20,000. So what? Can you give me a general idea of what we're doing and how to do it? Each time you want to go from 1 to finish the sentence in 3 words or fewer. Yes. I know you're just stretching, but I'm very sensitive to raised hands.
Well, we're just adding numbers
Mhm.
to get to a number down a bunch.
Great. So if someone said, well, if I wanted to go from 1 to 23, you would say to them, yeah, Nina,
Oh, isn't this on like video? They could watch the video.
you're quite right. So clever.
So you'll never have to be able to talk about anything ever again.
Watch the video.
Look at it.
Just look at it.
DVD or tape.
DVD or a tape? I bet you it's a tape. Well, I don't know. But I have a feeling that if we wanted to say this always works, if you start with 1, you can go up to any number you'd like. I just like a way of saying any number you'd like in fewer words than that. Ben?
You add 1 to that number and then you multiply it
Great.
by half the number
Oh, that's beautiful.
you wanted to go up to.
You add 1 to that number.
Then you multiply it by half the
We're going from 1 up to
that number.
a number. Which, the only, any requirements we have to put on this number? Yeah.
2.
Does it always have
It
to
could
be
be.
2?
It could be 2, but it needn't be. It could have been 10,000 or 20,000. So are we saying 1 up to this, 1 up,
Yep.
1 plus?
1 plus.
I get to do the
2
dot, dot,
plus-
dots.
Okay.
So you're saying when you want to add from 1 up to a number,
You just add 1 to that number and then divide it by
So-
2.
good, you
First.
add 1 to that number, and then,
Not divide it by 2. Multiply that by half the number.
and then multiply that by half that number. Are you getting tired of writing that number each time?
Yes.
Could we have a letter to stand for that number? What? X. Good. Are you saying X or S? X. X. So to add from 1 to X,
This is going to make my life much simpler. First add 1 plus X.
and
Then
then
multiply that by half.
by half of X.
Well, maybe you should make a key at the top.
Like,
Oh, well, the nice thing is, we can get this kit, because it says this works for any number.
I think.
So you have your little secret kit, and then somebody says, and the number is 42. And then
Can
you
we just
say,
try it with 3? 1 up to 3. 1 plus 2 plus 3. 3 is now playing the role of X. The answer is going to be add 1 to X, add 1 to 3, which we secretly know is 4, and then multiply that by half of X. 4 times, somebody said she didn't like fractions. Is that okay? Half of X. Is this right? Is this going to be correct?
Yeah.
3 plus 2 is 5 plus 1 is 6. 4 times 3 halves is
One.
good. 1 whole and a half.
Times 4. So 4 times 6.
4 times 1 is 4, and then half of 4 is 2. 6. So does this always work? To find out what it is from 1 to X, you add up 1 plus X and multiply that by half of X. Even when X is an odd number. Strange. Weird.
Yeah,
That's
you
pretty
like.
good.
Then do you then and you do the closest even number to that odd number, and then you add the one left over.
Get the closest even number to the odd number, and then add the one left over.
So the closest even
If
number to 3.
if we're going to stick with Eli's method,
Yeah.
where we're not going to add firsts and lasts,
Oh, right.
but where we're going to leave the last one out at the end, then we, yeah.
Okay, could do that. Can we do
This
a
is a little shorter to write, because it just says, all we have to get is 1 plus X, and put it in a little box, and then we have to times it by,
I worry about the times and
Oh.
the X looking alike. We need a new symbol for times.
No, you
Yeah, David.
could do the X the other way, like a. Oh no, that's a plus.
Yeah.
well, I know, I could do a really fancy scripty X.
Oh, pretty nice. Yeah. Yes. Oh. What were you going to suggest? We could use a dot for the times. That would be good.
I like dots.
Maybe even better. Yeah. Yeah, Nina.
For X, I mean, if we were just gonna keep times, we could have used Z.
Could have used Z.
That's 3 instead of.
Good, good, good. Elena.
What does X mean though? Like,
Oh, good question. What does X mean? I mean, it was you came. In a way, it means I don't know, but it's a specific kind of I don't know.
I don't know what number it is.
No,
Right.
no, but anytime you want a number, you could pop it in.
You could put in 17 for x, and then you'd be adding up 1 to 17. You could put in 4 for x, and then you'd be adding up 1 to 4.
You could put in 0 for x, and you could add from 1 to 0. Yeah.
What we're not sure about is whether you could put in a fraction for x. I don't know about that. Or a decimal. We could try
But you wouldn't
that.
like it if we put decimals, because you don't like decimals.
But listen, that's a good question. Could you put in a decimal for x? Lauren, what were you going to say?
Try it. Well,
It's an unknown number, or it's a
Excellent.
number which we just haven't taken the mask off of yet. We did when we put in 10 for it, or 20,000, or 100.
It's sort of like when you're making a law, like the signs that say anybody who crosses the street and steps outside the lines is going to get fined
$12.
$112. And it doesn't say if Lauren steps outside the line, she's going to get charged 100. They want to make it totally general, so that just says.
I want to do a
person,
completely
number.
different problem because it's 2 o'clock. Do you know that numbers come in shapes? Like triangles. Here's a number, which is a little triangle. That number being, thank you. What's the next triangle number after 3? Yes. 9, might be 9, because I take what I had and I put in one more row after it. Oh, 6. What do you mean it might be 1?
Wait, no, I'm talking to Colin about a
Oh.
circle might be 1. Just because it might also be infinity.
Right. But keep that 1 in mind. What's the next triangular number after 6? Yes.
9.
9? What do you think? 10? Other guesses? 12? 9, 10, 12. Doesn't this sound familiar? Nina.
12. You know, for the next thing that could happen after 3, it could be 4.
It could be.
And then it would be a square number.
Yes, let's do square numbers after we do triangle numbers.
Triangle numbers.
So there's a square number,
What about rectangle?
and we can do rectangular numbers too. Let's just check which of these 3 is right, or maybe they're all right, or maybe one of them is right. Yes, Danny. 10. Why 10?
Because if you add only 3 more, it'd be going straight down. If you added 4,
Oh.
it would be going up inside.
You're right. It's like piling cannonballs. You've got to fill up those spaces. 1, 2, 3, 4. So I guess the next one is 10. The next one after that?
15.
Good. Next one after that?
Let me think.
21. What's the one before 3? 1. It doesn't look much like a triangle, but it's a pretty good triangular number.
That's a pretty good pile of cannonball.
Yeah. Ever seen anything like this before? No. Yeah, Elena.
After 21, I don't even want to think of it.
No, what were you going to say?
I think.
Oh, you mean it's kind of like those diamond shapes. Diamond shapes. We can do diamond shaped numbers next. Yeah, Nina.
Kind of looks like Pascal.
Kind of looks like Pascal's triangle, whatever that is. What's Pascal's triangle?
It's a triangle. So that kind of goes like at the top. I think is 1, and then I don't really remember the rule, but
Yeah, I'm not sure I do. But keep it in
But
mind.
it is a triangle.
Yep.
So it's
so it's like a bunch of different numbers added in this special way.
Yeah.
I don't really remember exactly how it works.
Well, this is a bunch of numbers added.
I think
Yeah.
is it like 1 and then 2, 2,
Like that.
and then after that is 1 plus 2, and then 3 on the side.
It might be. I'm not sure.
I don't remember.
I don't either. If we go back to this, these are numbers, special numbers added in a special way.
Well, that's what Pascal's triangle.
Yeah. But these numbers 1, 3, 6, 10, 15. How'd you get 21? What? Oh, you added 6 to 15.
7, so that's 28 and 37.
And 36, what's the one after that?
45
What's the one after 45? Sound familiar? Ah. What is it?
This is the exact same thing as we were doing before. It's just adding.
Of course.
4 plus 5 plus 6.
You're absolutely right.
But if you were an ancient Greek, you'd much prefer to do it this way, because the Greeks have this sad, unfortunate trouble that their number system is pretty useless, in that this is an alpha and this is a beta, and 2 is a beta and 3 is a gamma, and so you don't get those nice things that we get about place system that lets you do adding and subtracting.
What you were saying about 0 at the very beginning, how useful it is for nudging numbers over. So we get triangular numbers, but then you mentioned square numbers. What's the? Yeah, you did. What's the next square number after 4? Next square number after 4? Yes. Okay. 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the very first square number? 1. I thought that was the first triangular number. Oh, okay. It's the first square number. It's the first triangular number. It's the first 5-sided number. So if the square numbers go 1, 4, 9. Yes. 12, is that right? Yes, Nina?
I think I know the pattern.
For the square numbers.
Yeah, for the square number.
Go ahead, tell me.
Okay, so it's like on the top of each, well, the first one is 1 on the top, for the second one is 2 on every side, and for the third one there's 3 on each side, and then 4, and then 5. You just get
Oh, so this should be 4 on a side, which will give you how much? 12?
after 9,
Yeah.
it's 12, and then
I mean, you're probably right. I just am not quite seeing it. 4 on a side.
25, and then
4 on a side.
no, it's actually 16.
Oh, it's actually 16. Okay. Yeah. Yep.
And the next one, 25.
And then 25. And then,
36.
okay. Here is a big question. Yes?
Yeah, it adds a row and a column each time.
It has a row and a column each time. That's nice. In other words,
So there was the 4, and it just got a friend.
yeah, you add a row and a column each time. What is the relation, if there is one, between the triangular numbers and the square numbers? Is there any way? Yeah, Lauren.
They both start with 1.
They both start with 1. Terrific. Anything else? Eli.
It might not really be like a relation, but
That's okay.
with the triangular numbers, you add 2, and then you add 3, and then you add 4.
Oh,
and with the
right.
square numbers, you add 1, and then 3, and then 5, and then 7, and then 9. Yeah.
Uh-huh. Yeah. So what you've done is you've gotten a relation among the triangular numbers, go up by 1 each time, add 1 more than you did the last time. You've gotten a relation among the square numbers, go up by the next odd number. Now can we get a relation between this row and this row, between the triangular numbers and the square numbers? Yes.
Well, it's kind of easy to find a pattern between both of them. That's another, like, relation between the two.
Yeah.
Is they each have a pattern that goes up a certain number each time. Each
Great.
step.
They each have a pattern that goes up by a different kind of pattern in each one.
Yeah.
This goes up by the next whole number, this goes up by the next odd number or something like that. Lauren.
And also for both of them, they start with 1 and then they add, well, for the triangles they add 2, and then they have 2, and then they add 3, and then they have 3, and then they add 4.
Yes. You know what? Ellen, you're so much better drawer than I am. Could you draw the triangular numbers as cannonballs better than I did? Because mine are sort of all over the place.
Do you want them like cannonballs?
Yeah. So it's a little less bloopy than what I did. That's interesting. You started at the bottom row, I started at the top. That's because you're...
It makes it more stable.
Yes, it does.
Usually when I pile cannonballs, I start at the bottom.
They're midair, they're going to fall.
Yeah, right.
You can draw a ground.
What if...
There we are. Phew.
What if we didn't have the numbers and just had the pictures? Is there a way of turning the top pictures into the bottom pictures somehow or other? I'm being very vague. If you, an ancient Greek, happen to walk by some cannonballs, yes,
I just saw that on those, each side has 4, and on here, each side has 4.
yep.
Like, if you look at the cannonball,
Oh, got you.
1, 2, 3, 4, 1, 2, 3, 4.
Take away 6.
Yeah,
Right.
In the middle. Oh, no, you wouldn't.
No, but that's neat.
No, so if I took this pile of cannonballs
Take away
and sort of pushed it
5.
with the help of a little concrete,
How big are Right.
Yeah. It's
Yeah.
this.
right.
Yes, Nina.
Okay, I have 2 things. The first thing is that sort of what Colin said, and sort of like, there are 4 or the same number on each side.
Mm-hmm.
So, for the same amount. And I don't think if you were in ancient Greece, you'd walk by that many kids.
You're probably right. In fact, you probably would walk by none.
have sling stones.
Yes. But you're right. What's interesting,
I drew them smaller this time.
I really like your idea that here again, there are 4 on a side. There just happen to be fewer sides. Yeah, Ben.
Like Colin's idea,
Mhm.
4 on each side, so you take away 2, well, just for the 4 on each side,
Yep.
you take away 2 of one side, and then 3 in the middle, so there's only 1 left in the middle.
Right. There, I mean like this one, the one left in the middle.
That's
You take away the 4 on one side, the 3 on the next, and the 2 that are left, and you're left with 1 in the middle. Hook that up with the 4 down here, if you can. I mean the 4 by 4, which is 16.
So if what we're looking for is how could you transform a triangle-y pile into a squarey pile? And Colin, is your name? Are you Colin? Yeah. So Colin's idea is, look, we already have the 4 verticals,
There's a connection.
and
What-
we've got the 4 horizontals. So there is a connection between the triangle shape and the square shape.
How can we get, well, we know how to get from this to this. You just push it over. How do we get from this to this? What do you have to do? Yeah, Ben.
you add the other 2 sides, and then you add the middle.
Great. You add the other 2 sides. You mean,
Do you want to come up and do it?
yeah, do it.
Like, that side and that side.
Uh-huh.
1, 2, whatever.
Yeah.
Like that, and then you add the 1 left in the middle.
So what was that
It's like a
whole thing you just
Yeah.
added? That's beautiful.
It's the other half of the square.
Yeah.
The other half of the square, not a full half. You added that thing to that thing. What is that thing? Does it look familiar? Yes, Ben.
Triangle.
It's a triangle. Which triangle? Yes, the other Ben. Yes,
Oh,
you.
okay.
2 Bens.
The 3 on each side.
Right. You're saying take 2 triangular numbers in succession, and you get this square number. I mean, it's only true here, I guess. 3 plus.
That's cool.
Yeah, weird.
Yeah.
10 plus 6 equals 16. It only works here, I guess. Well, What? Yeah, Ben?
It doesn't just work there.
Oh,
Just
The one in the 3 too.
back one.
yep,
Go right there.
yep,
Go back to this that smaller square number.
yep.
You take those two.
So any square number,
It works on both sides either way.
it works on both sides either way.
The 3 plus the 1, the 4.
Fantastic. Any square number is the sum of two triangular numbers.
That's interesting.
That is weird.
That's cool.
Fantastic. So 100, which is 10 squared, must be the sum of two triangular numbers.
Yes.
Namely, well, let's just do this one. 16, the 1, 2, 3, the fourth triangular number, the fourth square number, sorry. Fourth square number is 16, and it's equal to the 1, 2, 3, third and fourth. It's equal to 6 plus 10, the third and fourth triangular numbers. The fourth square number is the third and fourth triangular numbers. The 10th square number I know your minds are, yes, Ben. The fourth square number is the third and fourth triangular numbers. The 10th square number is the, yes, Ben,
Wouldn't it be the 10th and 9th?
10th and 9th triangular numbers. 9th plus 10th triangular.
So what is the ninth triangular?
The 9th triangular and the 10th triangular. Oh, let's do the 10th first.
Okay.
What is it?
10 plus 9 plus 8.
Which is?
Let's see.
Remember, this occurred earlier in your life. Yes.
10 plus 9 plus 8 plus 7.
I have a question.
Yeah, what's your question?
Why is the 9th triangle bigger than the 10th triangle?
Because of my terrible handwriting. I should have said the 9th triangular number. Cheating. The 10th triangular number is
55.
55. It's what
The
we.
9th is 50. No, the 9th is 45.
Now, if we're lucky,
No 10.
if we're very lucky, this will add up to 100. I don't think it does.
Oh,
Yes?
yes.
5 and 5 is?
And
So far, so good.
And then 9 is, plus 1 is.
Oh, it worked!
Yes!
That's great, everyone. Yeah, Eli.
30 seconds.
I have a question.
Yeah.
Do diamond numbers and single numbers do the same kind of thing?
Oh, what a great question. What about diamond numbers? What about rectangular numbers? What about five-sided numbers?
They probably all have. If we just found that
Probably all do.
squares, probably most other numbers.
Yeah. Think about this.
First of all, what do we think a diamond number would actually look like?
Ben. Since you're both Ben. Okay. Ben. What? Two triangles. A diamond number is two triangles. So the first, okay, what's the first diamond number?
1.
Is it 1 or is it going to be 2?
2. That's hard. I think it could be 2 or.
It's 1
It could be 1 or 2.
I get, yeah, it could be 1 or 2. We've got to decide how to think about
I
it.
think it could be
Yes, yes.
Is like a square basically the same thing as a diamond?
Oh, what a nice point. Yeah.
What do
So-
we think? That's more diamondy.
So that means that,
So we're not going to.
Start at 1 as a square form or as a diamond form?
by diamond, do you mean a square on its side, pushed over by the wind? Or do you mean something which is kind of like a diamond on a playing card? Not.
Could be either.
Could be either. So I guess we've got to. this is what happens in math when you get far enough along. We've gone very far today. You start asking, let's make our terms a little more precise. By diamond, do we mean square tilted sideways, or do we mean elongated thing? Whatever you decide on is great with us, and we'll just go and see where they lead to. Elena? You want the longer one? Okay.
Okay. So these are square diamonds.
Good. Square diamonds, good.
And these are going to be pointy diamonds.
Painted red.
And we think we start with one. What's the next one going to be?
Yeah.
I have something from Sarah has to do with the following. I don't know how to explain that. You know when you draw your diamonds, you kind of elongate them even though they are 4 squares still.
Yeah.
Ah.
They'll still be the same even if you elongate it like that.
So you could take this and just pull it apart a bit.
So like that one right there. It's still 4.
It's still 4, right. That's really nice. It's still a square. It's just gotten, it's been made of saltwater taffy and you've pulled it.
Outer areas and then squish them together.
Yeah,
And then put the other ones on top.
yeah, right.
So it's still 4. It might still be the same. It's probably still going to be the same.
So yeah, so diamond numbers in this way are really square numbers. 5-sided numbers might be something else. Eli?
But then the diamond in numbers is the same as square numbers.
Yeah. So
Is that disappointing?
Yeah, so then there's...
It's a tiny bit disappointing. Well, there's always 5-sided numbers.
Well, it means they have a very strong relationship. They're the same. There's some relationship.
What's the second 5-sided number? Don't sweat this one. It's an easy question. I'm not asking for the first. I'm asking for the second 5-sided number. Yes?
I don't think stop sign is a number.
10. Let's see. I guess I'm not totally sure how to draw it. Yeah, yeah. Well, Ellen's drawing it. What's the first 5-sided number? I think 1. Yeah, exactly. That's what I was thinking. In our old tradition, 1 is the first of the 23-sided numbers, or 5-sided, or 4 or 3-sided. And 5 might be the second one.
Yeah.
Unless you're worried about the space in there.
The third one would be 10. Right?
Let's check it. I think we've got to be very careful in drawing the
Can
next
we just
one up.
do it like crystal growing? Can we just make this crystal grow? So this one has 2 beads on it, so let's go out and have a 3rd bead. And then we want this side to have 3 beads on it. Is this going to work?
I think it is if we're... It gets hard to draw, doesn't it?
No, this isn't going to work.
No.
No.
Maybe we'll leave this as a question with you. Yeah, Nina.
I already noticed a pattern. So it's sort of just like 1, 5, 10, 15. So it's just like a multiple of 5.
If in
it
fact that's the
goes-
way they grow.
I think that's the way they go.
Okay.
Because when you did 1 and then it's 5, I think that's how we're going to do it. And then you add
Might
2
be.
in the little bubble instead, and then it would be 10.
Right.
Add another bubble, 15, and add another. It's like
Yeah, what if we did it the cheating way? So that we just put another bubble in there. Would that count for what you're talking about?
I think that's what Nina has in mind.
Yeah.
you just add one more bubble in each segment.
Uh-huh. We could call those the 5-sided numbers, and then it's going to go up by 5s, right?
Yeah.
Except for the very first from 1 to 5, which went up by 4.
One, you can't really. You have to when you have 1 and then you add. You can't really cheat on 1.
Yeah,
But you just have to add 4 more.
yeah. But from then on, it'll be 5. If that's the right way for them to grow. What were you going to say? Okay.
I think it is the right way.
Yeah,
Yep.
yeah.
Well, it's nice to actually get a paper and pencil and try various different ways of growing them.
Or you could just add 1 in each segment each time.
If you add one in each segment each time.
So like the first time, and after 5 you could add one more in one segment, and then it would be 6. But I like the 10.
Yeah, yeah, that certainly has a nice round feel to it. You have been absolutely fantastic, everybody. You've done real math.
And I don't know if you normally work for an hour and a half at a time, but that is an awfully long time to be sitting under bright lights and working
And on
one
camera.
subject all that time.
The backs of your heads are stars of stage and screen. Okay, thanks a lot. Thanks a lot, everyone.